All right. So yesterday we were trying to prove this decomposition theorem in an abstract setting. So the theorem is given parameters eta and delta greater than 0, there exists epsilon greater than 0 such that the following holds. All right, when I write like this before prescribing anything else, that means my epsilon does not depend upon any parameter which I will introduce later on. Let f from z mod pz to r plus be a non-negative function such that there exists v, another non-negative function with the following properties. What are the properties? First of all, it should dominate f. Shalom, it is clear, this side is okay? Second, norm v minus 1 is less than equal to epsilon. And third property, the L1 norm of V is at the most 1. Here, as usual, 1 is not really that important. Here, in this particular things, it is bounded by an absolute constant, you can modify things accordingly. So these are the assumptions. Then f belongs to okay. So then the function belongs to this closed convex set. K1 is, so K1 plus K2 is a closed convex set. Okay. And our assertion is that in that case, we can write down this function as a function from K1 and a function from K2. In order to prove this, yesterday we saw the following lemma. Suppose f does not belong to K1 plus K2, then there exists phi such that is greater than 1 for all f1 belongs to K1 okay? And for all F2 belongs to K2. Oh, okay. I have forgotten here while writing down a very important property that where is a norm such that is dual is an algebra norm. All right. So for all F2 belongs to K, okay? And then yesterday we proved this result assuming the simplifying assumption that suppose this phi which we have obtained here is a non-negative function. If that happens, then we prove the result. But now, in general, and in that case, we don't even need that the dual of our norm is an algebra norm. But a priori, we have been given such a function. There is no reason to expect that this phi will be non-negative. We have not constructed this function phi. We have just shown the existence of such a function. All right. So, okay, fine. So now, okay, this is 1, this is 2, this is 3. Okay. So the condition 3 is equivalent to say that norm, the dual norm, which is what? Supremum supremum of all these functions f less than equal to 1, and this is same as eta inverse and since this, okay, since for all these things are by this condition 3 are less than equal to 1, so therefore this is less than equal to eta inverse. All right. So norm of the dual norm of phi is less than equal to eta inverse. But yesterday we also saw that norm of phi infinity is less than equal to norm of phi star. If the norm is an algebra norm, then this algebra norm dominates the L infinity norm. That was obtained by taking the powers. Okay, so fine. So therefore, this is also less than equal to eta inverse. Since star is an algebra. So okay, now since phi is not positive, I define this function. Let phi plus be from z mod pz to r plus be defined as you will expect it to be, phi plus of x is equal to phi of x if phi is non-negative and 0 otherwise. Okay. Let j from r to r be similar function, be the function defined as j of x is equal to x if x is greater than equal to 0 and 0 if x is less than equal to 0. Okay. Then phi plus is nothing but the composition of the function j with phi. So now choose a polynomial p such that p of x minus j of x is less than equal to delta by 8 for all x belongs to minus eta inverse and eta inverse. We can choose such a polynomial using Wester's approximation theorem because minus eta inverse and eta inverse is a compact set. So therefore we can choose and j is a continuous function. So therefore we can choose a polynomial so that this polynomial is approximating this j function. Sorry? Delta over 8. Thanks. Okay. Then this implies that p of phi minus j of phi is less than equal to delta by 8 for all x. P of phi x for all x belongs to z mod pz. Why? Because norm of phi infinity is less than equal to eta inverse. So therefore for any x, phi of x will lie between minus eta inverse to eta inverse. So therefore p of phi x minus j phi will be less than equal to delta by 8 for every x belongs to z mod. In other words, norm of p minus norm of p phi minus j phi infinity is less than equal to delta by 8. Now understand that this polynomial does not depend upon your phi. It does not depend upon the norm. It does not depend upon anything. It is only depending upon delta and eta inverse, eta. How close you want to approximate the j function and in what domain you want to approximate this j function, this p depends only on those two parameters. because our epsilon will depend upon this particular polynomial p, which in turn depends upon only on this eta and delta. Now suppose this px is equal to summation I is equal to 0 to m ai x to the I, then I will corresponding to this polynomial, we associate another polynomial, namely Rp of x is equal to modulus of ai x to the I. So my claim is, why I need this polynomial is the following, that norm of phi dual is less than equal to the value of this polynomial at eta inverse. Okay. Why is that the case? So I have to show that norm of I is equal to 1 to m ai phi to the I star. Now this is less than equal to, using triangle inequality, summation I is equal to, did I start from 0, no? Okay. Mod ai using the fact that this is a norm and a triangle inequality. Norm of dual norm is a norm. So, and now I use the fact that this is a algebra norm. So therefore I can replace there by the powers can be taken outside with the inequality. Okay. But norm of phi star is less than equal to eta inverse. So therefore this is less than equal to summation I is equal to 0 to m mod ai eta inverse to the I. Which is exactly equal to since our polynomial did not depend upon, depended only on epsilon and delta, this Rp depended only on epsilon and delta, so whatever this number may be, it does not depend upon the phi, nothing else, but only on epsilon and delta. Yeah, eta and delta. Okay, having, so now I have all the ingredients to prove the result. So now let us prove proof of theorem. So f phi, on one hand this is greater than 1, okay. On other hand this is less than equal to f and phi plus. Why? Because f is a non-negative function. because f is a non-negative function, so I can ignore the contributions coming from the when phi is negative, and therefore this will be less than equal to f and phi plus. Now phi plus is a non-negative function, so therefore I can now, and f is dominated by v, so therefore this is less than equal to v and phi plus. Okay. Now I write down this as a 1 to phi plus v minus 1 phi plus. All right. So now this particular thing, we saw it yesterday, that 1 to phi plus, this is less than equal to 1 minus delta. Because 1 minus delta inverse into 1 will be a function in f2, this k2, k1. So therefore, okay. Now v minus 1 and phi plus, I again rewrite at a v minus 1 p of phi plus v minus 1 phi plus minus p phi. If I can show that this quantity is strictly less than delta, then we have obtained a contradiction. Because this is 1 minus delta and this quantity is strictly less than delta, so therefore 1 minus delta plus a number, so therefore, or I can show that this is less than equal to delta by 2. So then we will obtain a contradiction. So how do I obtain bound for this? In order to obtain the bound for this is less than equal to norm of v minus 1 into the dual norm of p phi. By definition of a dual norm, this is less than equal to norm of v minus 1 dual, norm of v minus 1 into norm of p phi. So this is epsilon and this is Rp. Okay. So if I choose my epsilon to be delta by 8, choose epsilon, then this is less than equal to delta by 8. Now the dual of L1 norm is an L infinity norm. So this is less than equal to norm v minus 1 into L infinity norm of phi plus minus p phi. Now, all right, because the dual of L1 is L infinity. Now, norm of v, the L1 norm of v is at the most 1. The norm of v1 is at the most 1, the constant function 1, is at the most 1, so therefore this is less than equal to 2. And there is a delta by 8. So total delta by 4. All right. So therefore, what we get, this is less than equal to 1 minus delta. This fellow is less than equal plus delta by 8 plus delta by 4. Okay. But this is strictly less than 1. So we get a thing 1 is strictly less than 1, which is a contradiction. So we obtain the result. Right? So now we will define the cut norm of Conlon-Fox and Zhao and show that its dual is an algebra norm. All right? But before I define this norm, let us obtain a necessary and sufficient condition for a norm to be an algebra norm. So lemma be a norm defined on some vector space. For what I am saying, there is no need for me to assume that this is a finite dimensional or not finite dimensional, it does not matter. And let's say B is the unit ball, closed unit ball. Okay? Then is an algebra norm if and only if B is closed under multiplication. So one way, so suppose is an algebra norm, then Fg belongs to B implies norm Fg less than equal to norm F into norm G, which is less than equal to 1, and hence F into G belongs to B. All right? So that proves one implication. The other implication Suppose f and g belongs to your vector space V. We want to show that norm of f g is less than equal to norm f into norm g. So if either of these functions are 0, then it is obvious. Other way is also obvious. Okay. So we can we can assume that f and g both are not 0. Then look at f by norm f. I can divide by the norm because f and g are not 0. They belongs to B. So by assumption, their product belongs, which means and that is exactly what we want. So therefore, a norm is an algebra norm if and only if the unit ball is closed under multiplication. So now let me define this Conlon-Fox-Jau's norm. So, okay, this I will define this norm and it may look somewhat artificial. If one wants to understand how this norm is come to the picture, maybe you have to understand certain things about the random graphs and the embedding of graphs into the other graphs. A task which I have myself not done it, so I cannot hope to explain to you. And moreover, not only that, for the lack of time, I will just restrict myself to, still one could see the easy implications of connections between Gauss theorem and graph theory. For that, I will refer you to Conlon-Fox-Jau's exposition on Green-Tao's theorem. Okay, and the relation between hypergraphs and the Geminides theorem, for which again I will refer you to exposition of Conlon-Fox and Jau on Green-Tao's theorem, and there should be many such expositions available. Okay, I will restrict myself to formally defining the norm and proving that its dual is an algebra norm. Okay, so we will define. So how we will do? We will define this norm and then obtain the structure of the unit ball with respect to this dual, and then show that that is closed under multiplication, which will prove that it is an algebra. So for any natural number r greater than or equal to 2, we will define on V is equal to this vector space. Okay. So before I do that, I need some notations. So given x is equal to x1 xr belongs to z mod pz to the power r. Okay. X minus 1 will denote so I forget the first coordinate, drop the first coordinate and let the remaining coordinate remain, and that will be my x minus 1. X minus 2 will be, now this time I keep the first coordinate but I forget the second coordinate. And same way, x minus I will be equal to all right. So notation is clear. Now given how many subsets? Okay. F belongs to z mod pz, so a function, and A1 AR subset of z mod pz to the power r minus 1. Let us look at this expression. So I am taking the average over the points in z mod pz to the r, okay? But my function is defined on z mod pz and not defined on z mod pz to the r. So what I will do? I'll apply f at the sum of the coordinates, okay? Then what this, why do I introduce these subsets? So I'll take I A1, x minus 1, I A2, x minus 2, so on, I AR, x minus n. All right. All right. So now I have to check that this is a norm. Okay. So norm. So for which what I have to check first, norm lambda f delta r is equal to, first of all I want to check this. Mod lambda But for any A1, A2, AR, when I multiply lambda, it will come out as a modulus. So therefore, when I take the supremum also, it will be a mod lambda. So this is okay. Similarly, triangle inequality is also holds, because for each A1, A2, AR, it will hold. And for showing that if f is, so now if f is 0, of course this is 0. There is no issue. What I have to show is that if norm of f is equal to 0, then this supremum is is not 0. So what I have to show? If f is not 0, then norm of f is not 0. So for that, I will leave it as an exercise that you can produce the subsets A1, A2, AR suitably chosen, so that this supremum for which this is not 0. So indeed, this norm is a norm. So now, okay, fine. So now I will now rewrite this norm in slightly different manner. So for that, first I take the example for when r is equal to 2. Okay. So what is norm f? So when r is equal to 2, let us look at this function again. X is equal to x1, x2 belongs to z mod pz square. This is what it is. Right? So therefore, now I can make the change of variable. I put x1 plus x2 is equal to z. Sorry? What? No, x minus 2 is what? X minus 2 is x1. So, okay, so when I do this, then I have this z, and x2 belongs to z mod pz, f of z, right? I'm making a change of variable, okay? But this also can be written, because for this function, it does not depend what the value of x2 is. So therefore, this is equal to f of z okay, which is nothing but f and the convolution a1 f with the inner product of f with the convolution function of a1 and a2. Okay? So in other words, this is equal to supremum over A1, A2, subset of Z mod Pz, modulus of inner product F with the convolution of A1 convolve with A2. It doesn't mean that for the R, it is the convolution of A1, AR. I will define some different kind of convolutions, and with that it will be. Okay? Okay, more generally, given more generally, given this R functions, we define YR is equal to Z and H1 of Y minus 1, S2 of, yeah, Y minus 1 will be, yeah. S2 of Y minus 2 and so on, HR of Y minus 1. Okay? So notation is all right? So because I am Y is equal to this Y1, YR, that is belonging to Z mod Pz to the R, I am only averaging over not all possible values of Y1, YR, but only over those ones such that their sum is equal to Z, as you do in the, when R is equal to 2, the convolution function. You can write down this thing is equal to, this is nothing but just let me just a small warning that here, though I have written down x1, x2, but it will be when you write down the average, they will be 1 by p and not 1 by p square, because you are averaging over x1 plus x2 is equal to z. So there is only one variable which is free variable. You fix the one, the other one is automatically fixed. So similarly here, when you are taking the average, there will be 1 by p to the power r minus 1 and not 1 by p to the r. So norm f norm f delta r is equal to supremum of A1 AR subset of Z mod PZ. This just follows from the definition. I have to only do this change of variables. Just like we did in the r is equal to 2, you just do this thing that x1 plus x2 plus xr is equal to z. Then when you write down, this will be exactly equal to, just like we did in the r is equal to 2, just make the change of variable and then you will get this. So I look at the functions of the form which is of the form this I AR convolution union minus so which is either the convolution of this generalized convolution of R many sets or it is a negative of the convolution of R many sets. Sorry? So I'm looking at the certain subset of the functions in V, and what are those functions? Those functions which can be written as a function which is for which you have a set A1 AR such that it is a convolution of these things, or it is a negative of this thing. Okay? So, fine. And then I consider those elements which can be written as a convex linear combinations of the functions in this particular set. Okay, maybe my notations are slightly bad, but I hope you understand what I'm saying. I have to take 0. Should I be taking 0? Yeah, okay, either you take the empty set to be a subset, so then it will be 0, or otherwise you introduce your 0. Union 0 maybe. Although in a sense 0 is already there, because if I take A1 AR to be empty set, then that convolution will be a 0 function. Okay? Okay, maybe I think I'll just state the things which are required to prove that the dual norm is an algebra norm. So what the two things, one thing is phi r is closed under multiplication. Is it? Phi r is closed under multiplication. And two, phi r is exactly equal to the unit ball. Of this. So let me prove two, and I will leave the one as an exercise for you to verify. I mean, it is easy. It's a Lemma 5.2 in Conlon-Fox-Zhao exposition. You can try to prove yourself. If not, then you can refer to the thing. I will just, in few minutes, how much time I have? 2 minutes. So it should be okay. It'll take 3 minutes. So if first of all, if I prove this true, then I have proven that the dual norm is an algebra norm. Because of the earlier result, when I say that the dual, so a norm is an algebra norm if and only if it is closed under multiplication. So okay, so I have to prove this too. Proof of two. So first of all, norm phi delta r by definition is what? Is okay, let me just say is equal to f phi. Phi belongs to this phi r. Because if you take the convex combinations of the function, the supremum is not going to increase. By definition of norm f delta r is equal to supremum of f belonging to this set, product of f with phi belonging to this set. But then I can take the supremum is not going to change. So what am I saying? I am only saying the following, that if suppose K is a convex set, generated by the set by the set A, so that it is a convex combinations of this, then supremum of f g belongs to K is equal to supremum of G belonging to A I don't know, okay, maybe I don't know whether I have to, at this moment, whether I need to assume that the A is a symmetric here. A is equal to minus A, if in our case, the A is symmetric. Okay, so supremum, the norm F is equal to this. It's time, no? It's over. Okay, fine. Yeah, okay, so tomorrow I will not prove this result. I will leave it again. This is an exercise for you guys.